Okay, so we have seen problems in the past where we've been talking about a particle, or in our case, the ferocious calculus beast moving along a number line, whether that was a horizontal number line or a vertical number line. And we had this invisible parameter t, which usually stood for time. And we are asked, okay, for what values of t is our beast moving to the right versus moving to the left? When is the beast at rest? When is the beast speeding up? When is the beast slowing down? And that could have been done vertically or horizontally. So we have a set of rules we've already established for one-dimensional motion, moving a horizontal direction or a vertical direction. Today you're going to take your parametric concepts from the last lecture and now apply it to two-dimensional motion. So now your beast is not moving along a line, your beast is moving in the coordinate plane. You need parametric equations to describe this motion because you have both a horizontal and a vertical component for any value of t. You're going to see many of the concepts carry over from the last lecture, just possibly some new notations or vocabulary. So first of all, the position of the beast in the plane was given by the parametric equations just like you had last class, x of t and y of t. You'll sometimes see these carrot tops, or whatever these are called, these hats, used instead of parentheses, and that's to tell you that you're talking about a vector.
I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah! Check out my new weapon. Piranha gun! Oh yes! Fires live piranhas. Ever seen one before? No, you haven't. I invented it. Do you want a demonstration? Oh! Ah! It's so difficult sometimes to get the piranha back inside.
For our purposes, a vector is going to be a line segment that points from the origin to whatever coordinates these functions pop out. Okay? Vectors can be placed anywhere in the plane, but for our purposes we'll place them with their tail at the origin and their tip wherever this function tells us to. So this vector, these two parametric equations, describe where in the plane the particle or the beast is at any time t. If you take the derivative of each of those, you now have a velocity vector. And the velocity vector, we usually like to place the tail wherever the particle is located so that we can see what direction the particle is moving. So the velocity vector is a direction finder, just like the velocity function was a direction finder in one-dimensional motion. This will tell you horizontally and vertically what direction is your particle or your beast moving, left or right and up or down. And then you have your acceleration vector, which just comes from taking the second derivative of each component. Harder to visualize in the plane, but questions are asked about it. Okay, so we have three types of vectors. Now let's talk about speed. In one-dimensional motion, we define speed to be the absolute value of the velocity. And one way of picturing that geometrically is if I have my velocity function, how far away from the origin is the velocity function. So if the velocity was -4, then it's 4 units away from the origin, whether horizontal or vertical motion problem. So in this context, we want to apply the same concept, but we're now in 2 dimensions. So if we want to take our velocity function, which is a vector, and ask ourselves how far away from the origin that is, then we need to use the distance formula because we now have 2 components. And so the speed in 2 dimensions is defined to be the square root of each component of the velocity vector squared, and then we add them together. This is also called the magnitude of the velocity vector, okay, or the length of the velocity vector. If I drew a picture, you had your curve in space somewhere, and then you drew the velocity vector with its tail at the point you were taking the velocity vector at. The velocity vector would point you in the direction of movement. Okay, so for example, at this specific moment, you would see a tangent vector, and it would point you in the direction that your particle was moving. So in this picture, the particle would be moving right and upward at this moment, which looks reasonable. And the length of this vector, okay, however long that vector is is the speed at which the particle is moving in the plane. And that's what this expression down here is finding. You have a similar derivation in the last lecture about how that's calculated using dx dt and dy dt. And one other point of interest for our particle or our beast is how far does it travel over a certain time interval. And that expression, that calculation is the same as finding the length of your parametric curve, which makes sense, okay? Because the curve is tracing out the path of the beast. So the length of the curve is the same as the total distance traveled. All right, I'm going to go ahead and jump into two examples just to show you what kind of things are asked on AP questions. So this first problem is talking about a kite. So I'll read through the problem real quick, and then I have a little module that shows you visually what's happening here. I have GeoGebra open. Our kite labeled K for right now time equals 0. I have a slider bar set up for T. And if you notice, if T is 0 in those equations, then your kite is at the origin. Okay, so I guess the person's on the ground, or the kite's on the ground, and then throws it up in the air and the wind catches it, and then things start to happen. All right, so for different values of T, the kite's going to start to rise or fall and move right or left. I'm going to go ahead and animate the slider bar so it runs through the time from 0 to 90 seconds. And it's got the trace put on it, so you're going to see dots being plotted. And you're also going to see a line segment that goes from the origin to where the kite is located. That acts as the position vector, and you can also visualize that as the string of the kite that's being let out. In this situation, these X values are actually how far away from the person the kite gets, and these Y values are how high the kites get. Because remember that T, which is not labeled on these axes anywhere, T is an invisible parameter that's controlling X and Y values. Okay, so our kite's flying upward and to the right. There's our string being let out, and then at some point the kite starts to lose altitude as it keeps moving to the right. Okay, I'll let that run a few times just so you can see. And we'll come back to this diagram a few times to verify the calculations that we actually come up with. You can kind of see how useful parametric equations can be for two-dimensional motion. Okay, so for example, at 65.5 seconds, that's where our kite would be. Okay, it would be located, looks like a little bit more than 8 units to the right of where we started and above 180 feet above the ground. And you can see how much string has been let out. More or less by that picture. Alright, so let's start to answer some of these questions here with calculus. So part A, how high is the kite at 32 seconds? It's not really a calculus question here. That's asking for the Y value of the kites, and we have the parametric equation for the Y value. All we need to do is plug in 32 to T. So the Y value would be negative 3 over 64 times 32 times 32 minus 128. And let's see, there's probably some simplifying we can do here to make these calculations a little bit nicer. 32 goes into 64 2 times. 32 minus 128 is negative 96. We can divide that by 2 and get negative 48. So I need to do negative 48 times negative 3, which is going to be, let's see here, 120 plus 24. So I believe it's going to be 144 feet. If I type in T equals 32, all right, it points me to there. And it looks reasonable that it's 144 feet. I don't have the calculation bar on, so we can't see for sure. But I'm going to go with that and say it's correct. Let me shrink that down. Part B says, at what rate is the kite rising at 32 seconds? So we're talking about the same moment in time. But now you're like a calculus question, okay, at what rate? And here we're talking about rate of rise, so that's going to be the rate of change of the Y value. So in other words, it's the derivative dy dt evaluated at 32 seconds. In this case, I think I want to multiply out the expression for y of t, if I have my choice. So let's see, we're going to have negative 3/64 t squared plus, let's see here, 128 over 64 is 2. So I think I'm going to have 6t. So that'll make my calculations a little bit nicer, I think. So dy dt, I could write y primed, but I don't want to confuse myself when I'm finding here. Dy dt is going to be, the second part is easy, that's a plus 6. And the 2 will cancel with a 2 in the bottom, so I'm going to have negative 3 over 32. Okay, And at 32 seconds, this will be at t equals 32. dy dt is going to be equal to, we're going to plug in 32, and the 32's are going to cancel nicely. And you'll have -3 plus 6, which is 3. So this would mean that your kite is rising at a rate of 3 feet per second. Okay, if we take a look, obviously we knew the kite's path continued to rise until somewhere over here, so that's reasonable to see. Now, part C is a little bit of a curveball, because it does not really match any of the concepts we've talked about yet, as far as parametric equations or vector motion here. So it's okay, because the AP sometimes will throw you a curveball once in a while and get people ready for it. At what rate is the string being let out at 32 seconds? Okay, so we saw the string. The string started at the origin and always was going to wherever the kite was located at any time t. And that string can act as the hypotenuse of a right triangle. Okay, so let's go ahead and draw in what is happening at 32 seconds here. And then we can generalize what happens. So we have our string, okay, and at any moment you have a y value and an x value determined by your values of t. Now, at 32 seconds we have some specific information. So I'll just draw another right triangle here. It's not the same one necessarily. Okay, so we've already found out that the y is 144. Okay, and I have a feeling already that my triangle is going to be not drawn to scale, so you have to forgive me on that. If we plug in 32 into the x, we're going to get out 4. So at that moment, how long is the string? Well, it's going to be the square root of 4 squared plus 144 squared. I confess to you that I do not know 144 squared in my head, so I'm going to have to go ahead and run to the calculator or go on to my scratch paper to figure that out. It'll be 4 times the square root of 1297. Alright, so let's head back over here and write that in here. 4 times the square root of 1297. Okay, now that's a specific moment. That's not answering the question. The question here is, at what rate is the string being reeled out at t equals 32 seconds? So we're trying to find the rate of change of s, okay, with respect to time, because the time is the independent variable here. So this is a related rate problem. Okay, so this is good to review at this point in the game. I need to set up a relationship that's evident in this triangle, no matter what, and then use the information I have right now to solve for what I don't know. So the relationship that's very clear in this triangle is the Pythagorean theorem, which is f squared equals x squared plus y squared. That's true no matter what, and that's actually how we found that value of the string length in that particular situation up to the right there. And we want to find ds dt, right? That's what we're after here. And we're going to find that by taking the derivative right now with respect to t. You could try to solve for s and get a square root over here. It's a little bit ugly, and I prefer not to do that. So I'm going to do it right now implicitly. So if I take the derivative of the left, I'm going to get 2s, and since s is not the variable that I'm differentiating with respect to, I need the chain rule, okay, times ds dt. That's where that derivative pops out from. Here you're going to have 2x, and again, x is not the variable that's independent. T is, so I'm going to multiply that by dx dt. That's an x, and then over here you're going to have 2y times dy dt. Hopefully it's all coming back to you. Alright, now, before we start plugging in particulars, we can cancel a 2 from every term. Alright, and now we need to have enough information to be able to solve for ds dt, which means we need to know s, x, dx dt, y, and dy dt. Some of these we've already solved for. Some of them we're going to have to come up with ourselves. Alright. S we know is going to be 4 times the square root of 1297. So I'm going to go ahead and write that in. We have ds dt is going to be equal to all this stuff over here divided by 4 times the square root of 1297. And we need to now know x. Well, we do know x at the moment 32 seconds up here is 4. Dx dt I'm going to have to calculate, I think. Won't be too hard to do that. And then y is 144. And dy dt we've already determined at 32 seconds is 3. Okay, and now we just need to find dx dt. How are we going to do that? We're going to take the derivative of the x function, dx dt, is going to be equal to, well, look, this is only going to be 1/8. It does not matter what the t value is. Got a steady movement there of our kite. Nice steady wind, I suppose. 1/8. Okay, so without simplifying, that's what you'd have to answer the question, at what rate is the string being let out at that specific moment? Okay, good review of related rate problems. At what time does the kite start to lose altitude? Okay, another way of thinking about that is, when does the kite reach its maximum? Let me go back to our picture here. Let's animate once again, and we can see that as the kite moves farther and farther to the right, at some point it does reach its maximum value, and we're asked to find what t value that occurs. Okay, so once we find the answer, we'll be able to check it pretty quickly here to see if we're correct. So what do we do here? Well, we need to find the local maximum for the y coordinates, correct? And I think we've already found the derivative right here. Dy dt is negative 3 over 32t plus 6. We're going to set that equal to 0. We're going to solve for t, and then we'll make sure that it's a local maximum, and then we'll have our t value to plug in to the y position function. Okay, so this will give us 6 equals negative 3, not negative anymore, it's now positive, so I moved it over to the other side, equals 3 over 32t. And let's see, we're going to divide by 3, gives us 2, multiply by 32, we get 64. So 64 seconds. And actually, we don't need to find the max height, it turns out, but let's verify that this actually is a max, which is reasonable based on what I've seen in the picture. We're going from 0 to 90 seconds. And here's our derivative. Let's plug in 2. Okay, that'll give us a positive. And if we plug in something like 80, would give us a negative. So that is a local max. Okay, so at 64 seconds, the kite starts to lose altitude. Let's see if the picture verifies this. If I type in t equals 64, okay, that looks like the maximum value, and we started to lose altitude after that moment. Let's take a look at least some parts of another one here. A particle moves on the unit circle so that any time t is greater than or equal to 0, the position is given by this vector. Okay, so this is the position vector. It tells you where you are in the coordinate plane. All right. Part A says find the velocity vector. So that's going to be just amounting to taking the derivative of each of those components. I'm not going to go through the calculation. I'm going to go ahead and pause the video and do that on my own and then put it in here because that's not anything new. Once you calculate and simplify it, you get these two expressions for dx dt, dy dt. They've asked for the vector, so you'll want to put the hats on the end of this. Okay, and I want to erase those notations. It wouldn't be terrible if you kept them in there, but that's what the vector would look like. Now, here's an interesting extension of what we already know about particle motion. In one dimension, if the particle is at rest, that means the velocity is 0. Well, we don't have a velocity function, we have a vector. So if the particle is going to be at rest, then both of these components need to be 0 at the same moment. Okay? At the same moment. Otherwise, it'll be at rest in one direction but not the other. We can see from the first component that t equals 0, the particle will be at rest in the horizontal direction, but t equals 0 does not make the second component 0, so the particle is never at rest. Okay, and I would say because dx dt and dy dt are not 0 at the same moment. Alright, and then part C, give the coordinates of the point of the particle, give the coordinates of the point that the particle approaches as t increases without bound. As t increases without bound means as t goes to infinity. So you're asked to find what is the limit as t goes to infinity, now of what? The coordinates of the point. Well, what determines the coordinates of the point is the position vector. So in other words, what does the x-coordinate approach as t gets huge? Well, the x-coordinate is determined by this function right here, and the y-coordinate is determined by the y-component of the position vector, which is right here. So what they're asking you, and what they're telling you, is that this position function, this beast, this particle, heads to a certain place as t goes to infinity. It doesn't actually just veer off into the sunset forever. So where does it head to? Well, we can do L'Hopital's rule in our head, or we can just kind of see what's going to happen here. I have a negative t squared as a leading term, and I have a t squared as a leading term. And so that coordinate's going to end up being -1. And I don't want vector notation now, necessarily. The coordinates are going to be -1, and over here I have a 2t and a t squared. The denominator is going to dominate. And so this particle heads towards the ordered pair -1, 0 as t gets big. I'm going to go ahead and create a quick model to look at this. T is set to 0. This problem says t is greater than or equal to 0. And we're going to let the slider run up at least up until 90, even though I can let it go as much as I want. But we're going to see where this thing heads. Okay, so t is still going up to 50, 60, 70, and we don't really see much more movement out of the beast. It is moving, but it's headed closer and closer and closer to that point, -1, 0. And if you remember what the stem of the problem said, the particle's moving along the unit circle. So if I make my axes 1 to 1, then the next time it runs through, you should see, there we go, half arc of the circle, and that's where your object is headed. Okay, so you have